and I'll ask people about these examples. Perhaps if there's a part where you are unsure how I came about my oxidation number, all I did was follow the basic rules that say elements by themselves, like zinc or copper in the second one, get an oxidation number of 0. If I have hydrogen or oxygen in a compound, it's +1 for hydrogen, -1 for oxygen. If I'm looking at something like NaCl, it's an ionic compound, so I realistically have 2 ions there, chlorine and sodium. Even if you forgot that, chlorine is way more electronegative than sodium, so you would give it its charge, -1, which would mean that sodium has to be +1. Just notice that in a couple of places like here and here, I indicated that you had to multiply by 2. So what I'm saying is the oxidation number of chlorine is -1, and each chlorine is -1. So if I asked you what's the oxidation number of chlorine in CuCl2, you would say it's -1. You wouldn't say -2, that's what it is when I count all of them together, but each chlorine is -1, and that's always what we're looking for. So if somebody asked you in either one of those compounds, what is the oxidation number, you would always say -1, not -2, just because there's 2 of them. Now, we can identify redox reactions with oxidation numbers, and I kind of alluded to this before. If the oxidation number of any atom or ion changes, then we know that redox happened. And one of the things that you will have to do is identify just, is this a redox reaction? Have electrons been gained or lost? And oxidation numbers are a really quick way to do that. If oxidation has happened, then the oxidation number will have an increase. So if I consider just this little half reaction with iron, its oxidation number would be 0 here and +2 here. If something gets oxidized, its oxidation number goes up, gets more positive. If reduction is happening, the oxidation number decreases. Chlorine's oxidation number when it's an element is 0. When it's an ion, -1. Remember, I'm considering each chloride ion and what its oxidation number is. The fact that there are 2 of them is fantastic. But whenever we ask for oxidation numbers, we mean for each atom or for each ion. So the oxidation number gets more positive or less negative when it's oxidation, less positive or more negative when it's reduction. You can tell just by that, and you could identify, say, the oxidizing or the reducing agent. So sometimes, without having to fully balance a big, long redox reaction, you could give oxidation numbers and just say, ooh, well, this thing's number went up. It's got oxidized, so it's the reducing agent. Ooh, this thing's number went down. It's a quicker way to identify the Ra and the Oa than maybe the long version that we've been doing up till now. So we know from before that in a redox reaction, the OA is always reduced. So the OA is the reactant. And can I just really highlight this? The OA cannot be something that is not present at the beginning of the reaction. The most common mistake I notice people make is they read what the question says, and the question will say something like, hey, you have potassium metal, and they'll tell me that potassium ions are the oxidizing agent. But we didn't have them. So you have to make sure you actually have this as a reactant. The oxidizing agent is the one whose oxidation number decreases, right? The OA gets reduced, so its oxidation number decreased, got more negative or less positive. In a redox reaction, the Ra is always oxidized, so the Ra is a reactant, something that was present at the beginning of the reaction, like that the question stated that we had, that contains an atom whose oxidation number has increased. Now, what if you assign oxidation numbers and none of them change? What does that mean? Means it's not a redox reaction. For example, I said way back in the beginning that double replacement reactions are not redox reactions. Nothing changes its oxidation number. Nothing gains, nothing loses electrons. So not every reaction in the world is a redox reaction. Some chemical reactions are not redox, and seeing that no oxidation numbers change would be good proof of that. Does anyone want to ask anything about that? So here's my question. Is the combustion of methane a redox reaction? If it is, identify the oxidizing and the reducing agent. So this actually makes us do two things. One, review how to write a combustion reaction, which you absolutely need to know. But two, give some oxidation numbers and identify oxidizing and reducing agents. So when I write a combustion reaction, I always use my fuel, in this case methane, as one of the reactants, and oxygen gas as the other. CO2 gas and H2O gas, unless it said it was a closed system, are my products. To make this balanced, I would add some coefficients. Now, is this a redox reaction? Well, if it is, something should change its oxidation number. So let's start by assigning all of the common numbers we can. In CH4, there's hydrogen. Hydrogen is +1 in a compound, and there are 4 of them, so I'd multiply that by 4. Oxygen as an element is 0. That's not a compound. That is just oxygen as an element. Over here, oxygen is in a compound, so it's -2. Hydrogen is in a compound, so it's +1, and oxygen in a compound. Now, perhaps you've noticed, but I can already see that something's oxidation number changed. So, before I even finish assigning oxidation numbers, I can say, yes, this is a redox reaction. Look. Oxygen went from 0 to -2. Has to be. Something happened. Now I'll finish assigning oxidation numbers so we can answer the question fully. In methane, carbon has to have -4 as its oxidation number so that overall this neutral compound adds up to 0. Over here, carbon has to have +4 as its oxidation number. For the same reason, we want our neutral compound to add up to 0. Now we just said the oxidizing agent, because it's getting reduced, should have an oxidation number that decreases, that gets more negative. Nope. Coefficients don't change oxidation numbers. We're looking at the molecule itself has to be balanced, and then if we have 2 or 25 million of them, it will be balanced still. So the coefficients are not super relevant if we're assigning oxidation numbers for now. If we want to balance the reaction, then of course, but when we're just giving the numbers, it doesn't matter. So the oxidizing agent gets reduced. That means its oxidation number decreases. So oxygen had to have been my oxidizing agent. Why? Well, it started out with an oxidation number of 0, and it went to -2. If I look at carbon, look what happened. It was -4, and now at the end of the reaction, its oxidation number is +4. Reducing agents have oxidation numbers that increase. So I would say that CH4 was my reducing agent and O2 was my oxidizing agent. Notice I didn't just say C was my reducing agent. It's part of a compound. The whole thing has to be the reducing agent. Notice I didn't include the coefficient in the reducing agent or the oxidizing agent because I just want the substance. Does anyone want to ask questions about this one? So we're going to do this one, which is a whole lot harder. So I'm going to let you have a few moments here to try. I want you to try assigning oxidation numbers using the rules, right? Elements that are alone are 0, hydrogen in a compound +1, oxygen in a compound -2. If you have a monoatomic ion, the charge that it is its oxidation number. But we're doing basically the same thing as with our combustion reaction. I'm telling you this is an oxidation reduction reaction. So give oxidation numbers and figure out what the oxidizing and the reducing agent are, folks. I'm just going to show you the oxidation numbers for all of these substances, and that way if anyone has any questions, they can ask. If I take this big polyatomic ion here, it has to add up to -2. Each oxygen is -2, and there are 7 of them. So I have 14 negative charges altogether. I have 2 chromium atoms that I can use to make up 14 positive charges. So if each of them were +7, then I would get 14. Is that what I want, though? No, I don't. And this is probably the most common thing that will happen, is your natural tendency to try to make it equal. I want it to add up to -2, so +6 is what we have to say is going on here. Then I have 12 positive charges, and overall, -2 is what that whole polyatomic ion has. Polyatomic ions are the worst for this because most of the time you want the positives and the negatives to be equal, but not in this case. Hydrogen's oxidation number as an ion is +1. Over here, I have -2 +1, then I have +1 times 5. So if I think about what that all adds up to, I have +5 and another one, so +6, -2. So overall, with all of those common numbers that I have +4. That means that those 2 carbons have to equal -4, so each of them has to be -2. Now on the other side of the reaction, I have a monoatomic ion. So it's an ion made of just one atom, so it gets the charge that it has, +3. I have oxygen and hydrogen in a compound. Now over here, and I think most of you recognize this, if you take the oxygen and the hydrogen that's already there, it adds up to 0. That will happen sometimes. That means that the carbon's oxidation number is 0 because it was already equal. So if I identify my oxidizing and reducing agent, I will notice that chromium went from +6 to +3. Since its number went down, its number was lower. What does that make it? My oxidizing or my reducing agent? Oxidizing agent. Oxidizing agents gain electrons, they get reduced. The carbon right here went from -2 to 0. So that makes C2H5OH my reducing agent. Now notice I had to pick the things that were on the reactant side. This is my reducing agent, this is my oxidizing agent, not the substances that are the products. Products can't be oxidizing or reducing agents. Anyone want to ask questions about that one? Now, if we're talking about disproportionation, the thing that you have to recognize is that in the beginning, the atom that's going to be the oxidizing and reducing agent will just have one oxidation number, but in the end, it will have two different oxidation numbers. So in this example here, if I assign oxidation numbers, oxygen would be -2, and there are 3 of them. So I have -6. This is +1. I want it to add up to -1 overall, so if each sulfur is +2, then it will add up to -1 overall. This hydrogen is just +1. This is an element, so it's 0. This is oxygen in a compound, so it's -2. Hydrogen in a compound, so it's +1. Oxygen in a compound, so it's -2. Hydrogen in a compound, so it's +1. In my compound at the end, since I want it to add up to -1 altogether, my sulfur has to be +6 in this scenario. So take a look at what happened. This substance contains specifically sulfur, and we said that to make those 4 positives, each sulfur had an oxidation number of -2. So sulfur, or +2, sorry. So sulfur went from +2 here to 0 there, but from +2 to +6 in the last compound. So what happened? Sulfur increased and decreased its oxidation number. HS2O3 negative is my oxidizing agent and my reducing agent. The line that I drew that goes to sulfur, just the S8, shows that I went from a positive number down to 0. So this is where it's acting as the oxidizing agent. The line that shows it going from +2 up to +6 is where it's acting as the reducing agent. Now sometimes, in fact most of the time, what you have to do is identify disproportionation. And this, I think, is a faster way than trying to balance a reaction, to identify it. Do you see that the same thing increased and decreased its oxidation number? If you do, then you know it was disproportionation. I'll just leave that.